Welcome to another one of my presentations on structural engineering. My name's Bob Johnson. I'm with the Structural Engineers Association of Illinois, and I've been doing this for 30 years, talking to children, students of all ages at various STEM expos. I've decided to record some of these presentations so anybody can see what I do in these presentations at various expos throughout the Chicagoland area. By the way, my handle is Engineer Guy SE. If you just look that up on the internet, you'll see also I have a Twitter page where I post information on STEM activities. So let's begin today. We're going to be talking about trusses. However, I've got to get to some basics. We're going to discuss tension. That is something like this, where you pull on a member. You can see this string is very strong in tension. If I put it in compression, like this piece of paper, and I push on it, or here I have a column and I push on it, it's going to buckle. Another force we have in structures is something called shear. That's when the forces align perpendicular to one another and the structure goes like that. Finally, we have something called bending. And that goes like this, where I have a member and it bends, and this is called bending. This is actually a combination of tension and compression. At the bottom here, it's in tension, and at the top, it's in compression. Notice one thing that's kind of strange about this. This is the same piece of cardboard, okay? If I turn the cardboard this way, same member, same strength. Now I'm going to try to bend it. I can't get it to bend because I've got compression up here and tension down here, and the distance from here to here is so much greater, I can't get this piece to bend. So let's talk a little bit about triangles. They come in all different shapes, and engineers love triangles. Why? Because we can't get them to move. Here's an equilateral triangle, and again, you can't get these pieces to move. What's interesting about a truss is there's no shear. There's no shear in the triangles, and there's no bending. All these triangles that we have in a truss are either in tension, pulling apart, or in compression, putting together. So let's put some triangles together. And what I've done is created a series of triangles. And you can see here one unique thing about this. I've paper clipped the triangles together. And I can put it on my supports here, and I can add weight and my truss bridge stands. You can see the shapes of the triangles, and this structure stands. Let's take another look at a different truss, different kind of shape. More of that equilateral triangles. But instead of putting it on here this way, I'm going to turn it over. But notice one thing I want you to be clear on. The bottom here, the triangles are connected with paper clips. At the top, they're not paper clipped. So if I turn this over, put it on my support, and you can see it barely stands because the triangles are coming apart. That's because in this truss design, the top is in compression and the bottom is in tension. I take the same truss bridge with the triangles, and now I can load it up The bottom is in tension, pulling apart. It's paper clipped together. At the top, it's in compression, so the triangles push together to one another. And here you can see it standing up. So this just gives you a simple demonstration to show you how truss bridges work. It's a combination of tension down here, compression here, and through the diagonals, they can either be in tension or compression. In the 1850s, the engineers came up with all kinds of ways to do these triangles, to design the bridges for railroad bridges. And here from my childhood days, I have one of my bridges that I had in my model train set. They can also be done in various types of support systems. Notice if I take my support here and put it over here, I can load it up here and it stands. Go to my other presentation on cantilevers and you'll see why. This is called a cantilever truss. If we put more weights over here, we can add more weights on there. It's very important that we keep these triangles. If we don't have the triangles and lose a triangle and go into a rectangle, and you can see again, see my presentation on triangles. We lose the triangle, and here I'm going to take the triangle out. We lose the support. So let me talk about a sad state of affairs back in 2007 in Minneapolis. Here we have our connection of members that are either in tension or compression. They come down and they're connected to a plate, and we call this a gusset plate. It's bolted through this plate, and the various forces in tension and compression travel through these members through this plate. And here we have the top cord being in compression, the bottom cord being in tension, and the members are connected together through this gusset plate. Sadly, on the bridge in Minneapolis in 2007, the bridge came down. 13 people were killed. What the engineers quickly discovered is this plate here wasn't thick enough to carry the weight. The bridge was going under renovation, and it had probably its highest load that it ever saw in its lifetime. So that plate is so thin, and it's got forces in it, it just crumpled. So that was a sad story. Back, one other little comment and then another sad story. You can take a look at my hand here. It's my wedding ring. People ask me, what is this ring, Bob? What are you wearing on this finger here, this pinky ring? And I tell them, that's my engineer's ring. It's something called the ritual of the calling of the engineer. Back in 1907, they were building a huge, gigantic, and where is that? Cantilevered bridge. up in Quebec. This thing was humongous, huge. It turned out it wasn't properly designed. The bridge came down during construction and 75 workmen were killed. After the bridge, and they discovered the problem with the design, they took pieces of the bridge and they manufactured rings. And this was up in Canada, and they created something called the ritual of the calling of the engineer, to remind the engineer, if they screw up, people can die. And this ritual came to the United States, and now they pass out rings. If you take the oath, you're given a ring to remind you, and you wear it on your pinky finger of your working hand. Notice here, I'm left-handed, so I wear it on my working left hand to remind me that if I don't design something properly, people can die. So we've got one other final truss bridge that I didn't discuss, but it's kind of unique, and it's called a Virendale truss, even though it's not strictly a truss, because here you can see I don't have triangles, but if I make these squares strong enough, it will carry the weight. But engineers do not like to use these for railroad bridges or highway bridges because they're not very strong. However, you'll see a lot of these types of bridges in pedestrian bridges where the loads aren't as great. And architects like to use them because you can put a window in here and not have a diagonal through the window. So here you have a little discussion on how truss bridges stand up, and sadly, how they can fall down if they're not designed properly. Again, just remember this. Up in here it's in compression, here it's in tension. We can also do this, and in some cases, aesthetically, with the bridge, we can have the roadway up here and have the truss below. So again, thank you. I hope you learned a little bit about trusses today. Again, my name's Bob Johnson. Trust me, I'm a civil engineer.